Good morning, dear students. Welcome to another session of Introduction to Data Structures and Algorithms. So in the previous session, we discussed regarding adjacency matrix, adjacency path, and a path matrix and the adjacency list. And one of the applications associated with the usage of graphs, that is the shortest path algorithm. So this is what we discussed in the previous sessions. Now moving ahead, let us discuss one of the important aspect related to graphs, that is graph traversal. So what is basically meant by traversal? Traversal is nothing but you move from one node to other node. That is, you in a systematic manner, you try to move from one node to the other node. So in, for example, if there are say 1, 2, and say something in this form, and there is some interconnection. So what you do is you want to move from node 1 to node 3. So in order to move, you have to move in a systematic manner. Say, for example, you'll be moving from node 1 to node 2 and node 2 to node 3, or else you'll be moving from node 1 to node 4 and 4 to 3. So this systematic manner of moving from one node to the other node is termed as traversal, which is referred as graph traversal, since the concept what you are utilizing is referred to the graph aspects. So this is one of the major tasks which are associated when we are using the graphs. So that is graph utilization can be seen in traversal or moving from one node to the other nodes with the help of the edges. Now, when we consider traversal, that is the graph traversal, we can have two methods. One is the breadth first search. It should be BFS, breadth first search, and depth first search. So which is DFS. Sorry, there is a typo error over here. So it is breadth first search and depth first search. So there are slight differences associated with these two and how they are implemented. So that we'll be discussing in the coming fourth sessions. Now, whenever we consider these methods, right, what happens is whenever we are traversing from one node to the other node in the graph, what happens is the nodes which are there will be in any of the following states. It can be in the ready state, it can be in the waiting state, it can be in the processed state. So these states actually refer to something we can, in short, we can term as that is these two things. That is visiting a vertex or a node and exploration of vertex or a node. So that is, these are the associations what we can look out for. So if it is in the ready state, it indicates that a node is ready to be visited. A node is ready to be visited. Waiting state, so a node is ready, but it has to wait for its turn to be visited. And processed state, in this one, what you are doing is you are indirectly looking out for the adjacency matrix, that is the neighboring nodes which are associated with the node which is under consideration. So these states refer to these two aspects, that is visiting a vertex or the node and exploring the vertex of the node. So exploration is nothing but identifying who are the neighbors of the nodes which we are considering. So let us look at those aspects when we discuss BFS and DFS. So here what happens is there will be a change in the state of the node whenever a node is visited and it is being explored. So that is what I can put forth. Whenever you visit a node and explore it, so that there will be a change in the state of the node. So indirectly, whenever you traverse a node, there will be a change in the state of the node. So that is what graph traversal will do to each of the nodes. So now coming to the first, that is breadth first search, which is BFS in short. Now what does this do is, in simple, what I can specify is These two give us information pertaining to what is called as minimum spanning tree. A minimum spanning tree. So both of them give information relating to minimum spanning tree. If you're using BFS, right, it is called as breadth first search minimum spanning tree. If it is DFS is used, it is called as depth first search minimum spanning tree. Now, what is the purpose of the spanning tree? If I just look at the previous graph right here. So what happens is in this graph, your main motto is to eliminate the loops. So here you can see that 1 to 2, 2 to 3, and 3 to 4 is there. So this loop I want to eliminate. So in networking concept, right, it is called as blocking port and forwarding port. So those all things come into play. So basically minimum spanning tree tries to avoid the looping which is happening. Now it has some reasons why you have to do that. Suppose if you're flooding a message into a network, I'm just taking the example of a network. If you're flooding a message into the network and each of the node in turn is again flooding the entire network. So you have sent some information to node 2, node 2 and node 4. Now what node 2 will do? Node 2 also will forward that or flood that message to its neighboring elements. So even node 4 also will flood the message. Now node 3 has received the message, again this will flood. So what happens is this keeps on flooding into the network. So this might make the network clumsy, that is it might congest the network. So such kind of things has to avoid it. So in order to avoid that, you can go for minimum spanning tree. So the network is this way. What is the minimum spanning tree for that network? So just an example I have just specified. So here what we have is breadth first search. So let us look at the concept which is associated with this. Say in this one, what is done is we consider the analysis. We start off from any of the node. It is not that you have to start from V1 only. So for example, if this is the graph traversal network, what I'm using, it is not that this is the first node what I should be visiting. It is not compulsion. You can consider any of the nodes present in this network, and from there you can go ahead with BFS analysis. So here from the starting node, what you do is you progress in such a way that you move along the adjacent or the neighboring nodes. That is, say for example, if I start with node V1, so this will be the starting node. Who are the neighbors of these two? Neighbors are 2 and 3. So I'll not be, I'll just for simplicity, I'll be referring it as 1, 2, and 3. So in this way, I'll be just referring it. So these are the vertices or the nodes. So from 1 to 2 and for this vertex or node, 2 and 3 are the neighbors. So first what you do is, first you visit this node, you identify who are the neighbors. After this step, so that is what you have done here. First you analyze the starting node. So in this case, I'll consider the starting node as the V1 node or the first node. And then what I do is I analyze by moving in the adjacent or the neighboring nodes. So that is node 2 and node 3. So once I have analyzed who are the neighboring nodes, right? What is the next step I should look forward is what will be the next neighboring node I'll be considering for the analysis. So I started off with node V1 or I started off with V1. I got to know that V2 and V3 are the nodes. After this, what I did is either I can go for V2, that is I can select this one, or I can go to V3. So if I go to V2, who are the neighbors for this one? So I visited this one. So first initially I visited node 1, which is the starting node. So from this one, I identified that V2 and V3 are the neighboring nodes. So once the neighboring nodes are analyzed from the starting point, next what we have to do is the neighboring nodes have to be analyzed. Neighboring nodes have to be analyzed. So I have analyzed this one. So node 1 is the starting point. Who are the neighbors for this? V2 and V3 are the neighbors. So I have visited this and analyzed it. Now what I have to do is, after this, whom I should visit. Whom I should visit. So I'll say, for example, I'll visit V2. So V2, if I'm visiting, I need to analyze who are the neighbors for this one. So it is V4 and V5. It is V4 and V5. So now again, you can see that there is a V3 which is present over here. So V4, V5 is given. So now I can consider the next node over here. So it might be 4. So for 4, 8 is the neighboring node. 8 is the neighboring node. So similarly, V2 if I just consider, V5 if I consider, V5 is having V7 as the neighboring node. So here what happens is whenever we are considering the graph traversal, right, there are different possible solutions for this. So if I'm implementing, say, a BFS method, right? So what I do is, in this case, I will be doing the analysis or the search by considering the neighbors. So I start with this point, I move to the neighbor. I start with this point, I move to the neighbor. I start with this point, I move to the neighbor. So here it is ended, but still there are few more nodes to be visited. So then what I do is I come back and start with this one. I analyze neighbor V3, then I analyze neighbor V6, and then I analyze neighbor V7, and then I analyze, say, V5. So there can be different possible solutions. It is not only one solution which is obtained. So remember, first you consider the starting node, analyze who are the neighbors, then jump to the next neighbor. It may be, if there are 10 neighbors, you consider one of the neighbors and then go ahead with the analysis. So here V2 is the neighbor, V2 is the neighbor for V1. So you jump to V2, then who are the neighbors for V2? It is V4 and V5. So you keep on continuing till all the nodes are visited. That is all the nodes you need to visit and analyze. So whenever you are doing BFS or DFS, so these two major steps you need to remember. So what is the case? First, you need to visit a vertex. You need to visit a vertex. So here I visited a vertex V1. Then I need to explore that vertex. So in BFS, right, you are exploring who are the neighbors. So for V1, who are the neighbors? V2 and V3. So next for V2, who are the neighbors? V4 and V5. So for V3, who are the neighbors? It is only V6. So for V5, who is the neighbor? It is V8. For V4, it is V8. For V5, it is V7. So you can see that all the vertices are being ticked over here. It implies that all the vertices are being visited. All the vertices are being explored. So that is what is being specified with BFS. You start with one of the nodes and then go with the analysis with respect to analyzing the neighbors. So that is what is specified. From the starting node, you realize who is the adjacent or the neighboring nodes. Once that is done, you need to consider one of the neighboring nodes and again start the analysis for that neighboring node. That is what you are doing. So this you continue until you visit all the nodes which are present in the graph. Now what happens is this method, if you just observe, right, here what I did, I observed that 1 is having 2 and 3, 2 is having 4 and 5, 4 is having, say, 8, 5 is having 7. Now if you just see again, I have to get back to 1 and see 3. So 3 is there, but for 3, who is there? 6. So what is happening? Frequently you have to keep the backtracking for the analyzed nodes. So you should analyze, since I need to check whether all the nodes are being visited or not. It is for that purpose you have to frequently have a backtracking done to all the analyzed nodes. So I analyzed V1. So V2 and V3 were there. I analyzed V2, V4 and V5 were there. Then I analyzed V4, V8 is there. So then I analyzed, say, V8, nothing is available as a neighbor over here. So now what I did is, again I went back, again I went back, again I went back. So that is, I have to keep the backtracking available in order to implement the BFS. So that is one thing what you have to look out when you're implementing BFS. And apart from that, you have to make use of the data structures for its implementation. For the implementation of BFS, right, you have to utilize the um, utilize data structure. So for what purpose? You need to keep the information pertaining to the neighboring nodes. Neighboring nodes. So now here, what is done is for BFS, right? You make use of a queue in order to store the node information. So why a queue? If I consider an example and explain, right, we'll get to know why queue has to be utilized. So here in BFS traversal, if I just look at the sequence with respect to this above graph. So if I apply BFS for this one, that is the first search. So which is the starting node I'll consider? Say I'll consider node V1, that is vertex V1. So after V1, you can see we have two nodes, two neighboring nodes, which is V2 and V3. So that is what is being specified over here. So next, I'll consider, say, for V2. Who are the neighbors for this two? These two? It is V4 and V5. So that is what is being written. So for this vertex, these two are the neighbors. Now, after this, you can see that we can have different implementation. So here, what they have done is they have backtracked it, and they have seen that V3 is the neighbor what you're considering. So for this one, what you can see is V6 is the neighbor. For V3, V6 is the neighbor. Now I move to V6. When I move to V6, who is the neighbor? V7. And when I move to V7, who is the neighbor for this? It is V8. Now here you can see that all the 8 nodes which are given over here are being visited. So this is the sequence when we apply BFS. This is the sequence when we apply BFS. So now, as I specified that you can have n number of solutions available for a given graph. So this is one solution. So for one, who are the two neighbors? It is 2 and 3. So I go to 2. Who are the two neighbors? In this case, it is 4 and 5. So for 3, who is the neighbor? 6. For 6, who is the neighbor? 7. For 7, who is the neighbor? 8. So that is what is being updated over here. So now what I can do is I can consider V1. There are two neighbors, V2 and V3. Now what I'll do is I'll visit V3 first and then go to V2. I'll visit V3 first and then I'll go to V2. So here what is happening? V1 is there. First you visited V2. First you visited V2 and then you went to V3. That is what is the information you are gaining over here. So but in this case, V1, who is the neighbor? V3 and V2. And for V3, who is the neighbor? V6. So here you can see that for V3, we have V6. So V2 and V3 and V1 are the neighbors for V3 and V2 are the neighbors for V1. Now I visit V3. When I visit V3, who is the neighbor? V6. Who is the neighbor? V6. And when I visit V2, who is the neighbor? It is 4 and 5. So that is what is being given over here. So then after this, either you visit this or this. So that will be the changes. So in this case, what they have done is they have visited V5. So for V5, who is the neighbor? V7. So that is what is being written over here. And for V7, who is the neighbor? V8. So by this way, you have visited all the nodes. So these are two possible solutions what they have given. So you can have different solutions also for any given graph. So this is how the BFS traversal sequence has to be obtained. So now here, if you just observe, what happens is you are visiting nodes level by level, level by level. So if I represent this as a tree, so since we haven't discussed that, in coming 4 sessions we'll be discussing. Say if I just consider a tree, there will be a root and there can be children associated, that is a branch associated with this. So this in turn can have again branches associated with this. This in turn can have branches associated with this. So here you can see that these are the levels. So here there is at this level there is one node which we call as the root node, and here I am say having got 2 nodes. So which is say this is say I'll tell as level 1, this is level 2, and this is level 3. So whenever you are using BFS, right, you will be looking for node, you will be visiting the nodes level by level. You'll be visiting the nodes level by level. So here, if I just consider for So if I just consider for V1, who are the two neighbors? It is V2 and V3. So I can write it in this form, V2 and V3. For V2, who are the neighbors? It is V4 and V5. V4 and V5. For V3, who is the neighbor? It is V6. It is V6. For V6, who is the neighbor? Or else you can go even for V5 also. So for V6, who is the neighbor? Say if I write it in this form, it is V7. For V7, who is the neighbor? It is V8. So here you can see that at first level, what I am having? I am having V1. That is what is being written. At next level, what I am having? V2 and V3. That is what is represented over here. At next level, what I am having? I am having V4, V5, V6. So that is what is being represented over here. At next level, what I am having? V7. That is being represented. At next level, what I am having? V8. That is what is being represented. So this sequence, what I have obtained, right? This sequence, what I have obtained. So you can obtain the solution for this by building a tree also. So what you can do is, so for this one, you build the tree. For this one, you build the tree. Say you write V1. V1 is having two neighbors, V2, V3. And V2 is having two neighbors, V4, V5. And V3 is having a neighbor, V6. So which falls in this level. Then you can change this one. That is V5 is having a neighbor, V7. So once already it is done, it is being visited, no need to go for V6. So V6 neighbor already it is there. So you represent actually with the dotted lines when you implement that, right? So this is actually a cross edge. This is actually a cross edge, since there is from V5 also you can reach V6 and sorry, V7 and V6 also you can reach V7, right? This is called a cross edge. These are the edges. Since this one already there is a establishment, so no need to have a connection. This is actually called a cross edge. So now so V7 is having the neighbor, or you can have even V4. So V4 is having the neighbor V8. So you can have even in this form. So here for this one, right, you write all these nodes. So for if I consider this one, right, what will be the sequence? So V1, so which is the first part, then I am having V2, V3, then V4, V5, V6. So V4, V5, V6. So this level, then the last level. So it is V8, V7. So this is another sequence. You can see that this sequence is different from these two. So it goes on how you represent it. How you represent it. Okay. So this is what we have for say BFS implementation. So remember for BFS or DFS, two things are important. One is visiting a vertex and one is exploration of a vertex. So here in BFS, right, identifying the adjacent node becomes important. So that is the logical aspect what you have to look out for. But for DFS, it will be slightly different. It will be slightly different. So what does visiting node imply? You consider a node and you explore that node. That is, you try to identify who are the neighbors. So that is what is being done in BFS. So this will be coming up later. So this we'll discuss later. So now let us discuss with respect to depth first search, DFS. So in DFS, what we have, in this case, we traverse the graph in, say, in a path kind of thing. So previously what we did, we traversed from one node to its neighbors. We identified neighbors and then considered the neighbors and then we did the analysis. But in this case, right, we refer to what is called as actually pre-order. There is some concept called as pre-order in trees. So now we'll not discuss that part. So just we'll try to keep it simple. So in this one, we start off with one node. We start off with one node. We explore who is the neighbor to this. So here you can see that there are two neighbors associated with these two. Now what I do is, out of these two neighbors, I'll consider one of the neighbors. So in this case, I might go and consider V2. I might go and consider V2. So what is this specifying? You have visited V1 and you identified that there is a neighbor V2. So what I did is I jumped and visited V2. I jumped and visited V2. Now, now I explore who are the neighbors for V2. Who are the neighbors for V2? So in neighbors for V2, it is V4 and V5. So I got to know that there are two neighbors. Now what I have to do is I have to go and jump to one of these neighbors. So what I'll do is I'll go to node V4 or the vertex V4. So this is the vertex what I'll be visiting. This is the vertex which I'll be visiting. So for V4, who are the neighbors? So in this case, only V8 is the neighbor. So what I do is I go and jump to V8. I go and jump to V8. So after V8, you can see that there are no neighbors. So this is the end of this path. This is the end of this path. So previously what you did in breadth first search, you identified the neighbors, and for those neighbors, you kept on updating. But now what you do is once you identify any one of the neighbors and I haven't visited that neighbor. So in this case, this was the path which I traversed. So V3 still I haven't visited, but I know that this is a neighbor for this, but still I haven't visited. So here V1 is visited, V2 is visited, V4 and V8 all are visited. Now what I have to do is I have to again trace back. I have to again trace back. Now again what happens is since you're tracing back, what happens is you come back to V4 first. And from V4, is there any other neighbor? No. So then I come back to V2. From V2, is there any other neighbor? So you can see that V5. And still it is not explored. I haven't visited this. So what I do is I go and visit V5. I go and visit V5. So this one is visited. So this one is the neighbor. So I jump to this point and I check who is the neighbor for this and whether that node is being or vertex is being visited. So here I see that V7 is the vertex and still it is not visited. So I jump to the next node. So which is V7. So V7, who is the neighbor to this? It is V8. Is it already visited? Yes, it is already visited. It has been already been tick marked. It is already visited. So here what it implies, this is the end of this part. You have reached the depth of that path. You have reached the depth of that path. So next, what you do is again you trace back. So you go to V5. Is there any unexplored or unvisited node to this one? So V7 was the only, and you have already visited this. So again you go back V2. So V2, V4, and V5 both are visited. Again you go back to V1. So you can see that for V1, V2, and V3 are the neighbors, but V2 is already being explored because it has already been visited, but V3 is not being explored or not being visited. So therefore what you do is you go to V3 and you explore, you visit V3 and you explore the neighbors of V3. So who is the neighbor of V3? V6. So is V6 being visited? No. So what you do is you jump to this one and you analyze, you visit V6, and you analyze the neighbors. So for V6, who is the neighbor? It is V7. It is V7, but V7 is already visited. So what happens is this indicates that this is the end of the path. And again, you trace back and you get to see that all the nodes are being visited. All the nodes are being visited. So in DFS method, what you do is you visit the nodes which are present in the graph in different paths. So that is what you specified. So first I visited like this, then I visited like this, then like this. So different paths I traversed and then I obtained the DFS. So you visit the nodes each in different paths. That is what you are doing. So you begin the analyzing, you begin the analysis from any of the nodes, consider it as the starting node. And once you identify that, right, you need to identify who is the neighbor and you have to jump to that neighbor. That is, you complete that entire path. You complete that entire path. So V1 is having V2, so jump here. So V2 is having V4, jump here. V4 is having V8, jump here. So this entire path is being completed. Again, you have to traverse back. V5 was pending, so V5 and V7. So already this is being visited. So this path is also complete. So that is, you start to the end node. You have to traverse from the start to the end node of that path. So that is what you are doing over. So this process is continued until all the nodes are being visited in this process. So that is what is being done. In previous breadth first search, what you did, you considered V1. So who are the neighbors? V2 and V3. So out of V2 and V3, so both are specified, V1, V2, V3. So these are the neighbors what we have. So for V2 or V3, anyone you can consider. So if I considered V2, right, V4 and V5 were the neighbors. So that is at level implementation we had this. This is level 1, this is level 2, this is level 3. So on it continues. So that was what was being done. But in this case, you are updating in the path form. You are updating in the path form. So all the nodes have to be visited, then only you will be completing the depth first search. Now, what does DFS require? Similarly, as we saw in BFS, right, we require a backtracking even in DFS. So that is what we can observe. And for implementing DFS, right, you have to use stack. You have to use stack. So in queue, what is the logic? In queue, if you just see, so if I have a queue, right, here the elements are inserted at the rear end and they are deleted from the front end, and it works on the principle first in, first out, first in, first out. And if I have a stack, I insert at the top end of the stack, and from top end only I delete. That is, it works on the principle of last in, first out. So you have to use a stack for implementing DFS and queue for implementing BFS. So that is what you will be looking forward. That is why you will be using these two is in order to identify which is the next node I need to consider. So that is what I'll be looking forward. Okay. So what is the traversal sequence for this given graph? So you can see that the first node what I'm considering is V1. First node which I'm considering is V1. Uh, uh, who is the neighbor for this first node? It is 3 or 2. So you can either go for 2 or either go for 3. You can go for any of them. So in this case, what I'll do is I'll go for 2. I'll go for 2. So this one is having 2 possibilities. I'll go for 2. This one is having 2 possibilities. So 4 will be the next node. So for that is what is being specified. So I go to node 4, that is I visit node 4 and explore that V8 is the next node which is available. So therefore, this is the node which I'll be considering. That is what is being specified. So this gives me one path. This gives me one path. Now what I have to do is I have to see who is the previous node. That is, in order to trace back the entire nodes which are present, right? I have to move back. So 4. So for 4, is there any other neighbor present? So V8 is the only neighbor and it is already being visited. So again, I trace back and I see that V2 is there. So for V2, V4 was there. V4 already I have visited. So what is the next this thing? V5. So that is what is being specified. So for V5, when I visit, who is the neighbor for this one? It is V7. So it is unvisited, that is we haven't visited to that. So V7 is the next node which will be present. So now V8 is there. V8 is already being visited. V8 is already being visited. So therefore I again go back. V5 is there. So there are no other neighbors. I go to V2. There are no other neighbors. Then I go to V1. There are no, there are 2 neighbors. One is already being visited. So now next what I do is I visit V3. I visit V3. So next, who is the neighbor for this one? I move to 6. That is V6. So in this way, you can have different possible sequences for BFS, DFS applications. This is DFS. This is DFS. DFS visits nodes path by path. So that is, if one path is complete, then it traverses the nodes and sees whether any other possible thing can be done over here. So that is what is being done. So in this case, what you're doing, you are traversing node by node, level by level. But in this case, you are going path by path. So this is actually a DFS. It is going path by path. So that is the algorithm what they have specified over here. So this is all for this part wherein we have discussed BFS and DFS. So let us meet in the next session wherein we'll discuss a few more examples pertaining to BFS and DFS. Thank you.